So in this video, we are going to answer this question: why there is no FCT Bravais lattice? So here I am assuming you understand what is lattice, what is Bravais lattice, and then in this case this FCT would mean face centered tetragonal Bravais lattice. So what is this face centered tetragonal? In case of tetragonal Bravais lattices, you have the condition, the lattice parameters A, B, C as such that A is equal to B, not is equal to C. And then the angles alpha is equal to beta is equal to gamma is equal to 90. So these vectors A, B, C will be orthogonal to each other, meaning 90 degree with each other, but the length of the A, B vector will be same, but with the C other vector will be not is equal to ABC, AB. So this video might get a little longer, but this is interesting. So let's first see what is a face-centered tetragonal. To do that, let's first draw a simple tetragonal, right? So a simple tetragonal would be like this. You have a crystal system where the unit cell would look like this. So that's a unit cell, and with the atoms sitting at the corners, then that's a simple tetragonal. Now in this case, this length is A, let's say this is B, this length is A, and this length is C. So that's little longer. So these two are same but not is equal to this. This is different. So when only the corner atoms are there, simple tetragonal. Now if I draw the same unit cell, but now what I will do is I'll put the atoms at different positions. So the usual ones are there, the corner atoms are there, but if I put 6 more atoms on the faces, so this is at the top face, this is at the background face, and this is at this face on the right hand side, this is at the bottom face, this is at the background, this left hand side face, then this is at the front face. So you have 6 atoms, and that makes your face centered tetragonal. Again, this is B, this is A, and this is C. These angles are 90 degrees here, here, and these angles are 90 degrees, right? So that's your FCT. This is simple tetragonal, this is face centered tetragonal. The other one that you can get is the usual atoms are at the corner, the angle between the axes are 90s. This is B is equal to this is A, this is C, not same. So A is equal to B, not is equal to C. These angles are 90 degrees. So these 8 atoms are there, and then there is a center atom, so body centered atom, which is at the center of this unit cell. The diagonals will pass through these atoms. So that's your BCT. This is FCT. This is simple tetragonal, face centered tetragonal, BCT. There could be another one, and that is called, I am going far beyond the question asked. If you are answering this in an exam, you don't have to discuss all of this, but you can make your discussion between these two. We'll come to that. So that's another one. If I only have now 2 more atoms, one at the top, one at the bottom, then I'll have a base centered tetragonal. That is body centered, this is base centered tetragonal. So that's also a possible lattice, Bravais lattice. But generally, you don't see that. What you see is only this one and this one, not this, not this. These are absent. So our question is why this is absent. Also, as an extension, you can also answer why this is absent. These Bravais lattices are absent. Now to answer this, let's draw this one once again, but we'll do that a little carefully, because now the drawing or the diagram is more important for you to understand. So let's draw the face centered tetragonal. So these are the atoms at the corners, and what I am doing, I have 6 atoms at the 6 different faces. Just to make it neat, I am not drawing all other face centered atoms, only these 3. This one at the top, this one at the bottom, like this. This one at the top, and this one on this left hand side face, this one here, right? The other atoms are there, but I'm not drawing it, just to make it simple. Then what you have to see is, you extend this lattice, because you see lattice is a part of the crystal, and crystal is an extended structure of the unit cell. So you repeat several unit cell and then you get a crystal structure. So here is the unit cell. The next unit cell, you can also draw the unit cell on the other directions, but you can repeat what I'm going to say with these 2. So you have the atoms on the adjacent unit cell. Also, I'm going to draw only these top and bottom atoms. There are other atoms on this face, on the back end face, on the front face, and so forth. I'm not drawing those again. Do remember that. So now what we can do is, let's do a trick. Connect this top and bottom, connect this top and bottom, connect this one, connect this one, connect this one, this one, this, and this. There is an atom here. So I also connect this one, also connect this one. Right, so what do you see here? If you look carefully, this red unit cell that I have drawn, You see, it's like this one on the top, this one on the bottom, and there is this one atom at the center of this. If you consider this to be a unit cell, you see, there is this center atom, so this becomes the body centered. So the red one is a body centered tetragonal, but we started with these green ones as face centered tetragonal. So you see, what happens is, if you start with a face centered tetragonal, then you can see that within the face centered tetragonal, the body centered tetragonal is there. So in other words, this face centered tetragonal and body centered tetragonal are basically the same. You just reorient your unit cell and then you get the other one. Likewise, you can start with body centered tetragonal and then you can form the face centered tetragonal just by repeating the nearby unit cells and then reorienting the unit cell. How am I saying this a body centered unit cell? Because you see, this length and this length are same. This length and this length are same. This length and this length all are same. Similarly, the top one. So if I consider this to be A, this to be B, so A is equal to B, right? So this is A, this is B. A is equal to B, but this length is different, right? So this is C. So you see, that's a tetragonal unit cell, but this is having an atom at the center, so BCT. So because FCT, BCT are both basically the same thing, then question comes, why we choose BCT, not choose FCT? Generally, there is this rule that if two unit cells are equivalent to each other, they're basically representing the same lattice, same crystal structure, two unit cell representing the same crystal structure, then you choose the one with the lower effective numbers of atoms. Now you know, body centered unit cell would have two atoms, effectively two atoms in its unit cells, and face centered unit cell would have 4 atoms per unit cell, effectively. Because face centered atom has more atoms, so you don't choose that. That's how we go along, right? So also this actually answers your body centered, base centered system, right? So in the case of base centered, if you have only the base, like what we have drawn, ignore this one, right? So I have only the base centered, so this top and bottom atoms are there. So what do you see? If I have this base centered tetragonal, then I can see, if I connect these ones, then I get this simple tetragonal without this one, because base centered do not have this, huh? So again, base centered has more atoms, effective numbers of atoms are more, 2 in this case, and simple tetragonal has 1, so we choose simple tetragonal. Similarly, you can ask the same question for simple cubic or cubic unit cells. If you have cubic unit cell, so cubic unit cell, you have simple cubic, face centered cubic, body centered cubic. You do not have base centered cubic. You don't have that. You can also start with base centered cubic, and you will see you will end up with one of these. So that's your exercise to figure it out. Okay, so with this we end our video where we have answered this question, why there is no FCT Bravais lattice. Right? So remember this statement, and that's the basis for these things, not having face-centered or base-centered tetragonal. Similarly, not having base-centered cubic. Okay, thank you.